So in this lecture, we'll be exploring what threads are, why they are so important, and how they allow our computers to perform multiple tasks seamlessly at the same time. Let's get started. What exactly is a thread? As the slide says, a thread is a path of execution within a process. The textbook gives us a more technical definition. That is, a thread is the basic unit of CPU utilization. Every thread has its own thread ID to uniquely identify it, a program counter which keeps tracks of which instruction to execute next, a set of registers which store the current state of its variables, and its own stack which used for function calls and local variables. Now, the really important part is what threads share. As you can see in the diagram, all threads that belong to the same process share the process's code sections and data sections and other operating system resources like open files and signals. On the left, you can see a traditional single-threaded process. It has one program counter, one stack, one path of execution. On the right, we have a multi-threaded process. It still has one program, one shared pool of code and data, but it has multiple threads, each with its own registers, stack, and a program counter. This allows the process to perform more than one task at a time. A great example can be your web browser. One thread might be rendering a web page that you see, while another thread in the background can download images or videos. So, why go through the trouble of creating multiple threads? There are basically few benefits. So, one is responsiveness. In an interactive application, multi-threading allows a program to keep running even if one part of it is blocked or doing another long calculation. For example, if you click a button in an application that starts a time-consuming operation, a single-threaded app would freeze and become unresponsive. But in a multi-threaded app, the long operation can run in a separate thread, but in the main thread can stay responsive to the user. Another one is resource sharing. As we just saw, threads share memory and resources of their parent process by default. This is a huge advantage. For separate process to share resources, the programmers has to explicitly set up complex mechanisms like shared memory or message passing. With threads, it's automatic, allowing different threads to work on the same data within the same address space easily. Another one is economic. It is much more economical to create and manage thread than it is to create and manage full processes. Creating a process is basically costly. It requires the OS to allocate a significant memory and resources. Since the threads share most of these resources, they are much lighter and faster to create. Similarly, switching the CPU's attention between threads, which is also known as context switching, is typically much faster than switching between processes because of their overheads. Another one is scalability. So this is where threads really shine on modern hardware. Most computers today have multiprocessors or multi-core systems. A single-threaded process can only run on the one CPU, no matter how many are available. However, a multi-threaded application can have its thread running in parallel on different cores, leading to a significant performance increase.